friends, welcome to the channel Physics by IITians. This is another important problem series of statistical mechanics, and in this video we will learn the basic concepts of statistical mechanics by solving numericals. This video is going to be very important for you, and we request you to stay updated with our all the videos covering the statistical mechanic lectures and the probability lectures. Both are actually very much related to each other. That's why we request you to stay updated with this two lecture series videos. And another important announcement that we are going to arrange the second full length test, and the link will be activated from tomorrow. The questions are actually tough. Don't be disappointed if you can't attempt the questions, because the solution paper will be available, and also you will learn a lot from it. Okay, and the question paper actually is based from the NET paper and the TIFR paper, so it will be very much helpful for you. So let's start the video. So the first question I would like to discuss, that is, an electron gas obeys the MB statistics. The average thermal energy in electron volt of an electron in the system at room temperature is how much? First of all, there is something, the main concept here, that the question is very much easy, okay, but there is a problem with the dimension. I mean, in this question nothing is written. It is not written 1D or 2D or 3D. Okay, so what should I take? The electron gas, that is MB statistics, we usually will take the three-dimensional case, not the one-dimensional case. Okay, if it is mentioned that it is one-dimensional or two-dimensional, then we can take that. Otherwise, we'll assume that these are all the cases of the three-dimensional, that is the real case that we observe. And another, you have to understand it, if the room temperature, it is mentioned that 300 Kelvin, but what if it is not mentioned? Then you have to take it 300 Kelvin, that is 27 degree centigrade. Okay, if just in this question paper, if it is only mentioned that an electron gas obeys the MB statistics, the average thermal energy of an electron in the system at room temperature is how much? You have to take at room temperature means 300 Kelvin. Okay, so the options are available: 0.039 electron volt, 0.051 electron volt, 0.07 electron volt, 0.015 electron volt. Now for the three-dimensional case, we apply equipartition law, and for the 3D case, the average thermal energy will be half kBT plus half kBT plus half kBT. That is 3 by 2 kBT, because ideal gas, we don't have to take the potential, we take potential equals to 0. So only the average energy is equals to the average of the kinetic energy. Okay, and for each the dimension, along x it is half kBT, along y it is half kBT, along z it is a half kBT. That is giving you the total 3 by 2 kBT. Now kB, the value of kB is 1.38 into 10 to the power minus 23 joule per Kelvin, and T is 300 Kelvin. Okay, so 3 by 2 kBT, it will give you 3 into 3.18 into 10 to the power minus 23 into 300 divided by 2 joule. Now the question here asks that the average thermal energy in electron volt unit. So from joule you have to calculate the average energy in terms in the unit of electron volt. So what you have to do, you have to divide this quantity with electronic charge, that is 1.6 into 10 to the power minus 19. Okay, so 3 into 1.38 into 10 to the power minus 23 into 300 divided by 2 into 1.6 into 10 to the power minus 19 electron volt, that gives you 0.039 electron volt, and option A is the correct answer. So from this question, one thing you have to remember, that whenever there is no dimension is mentioned, you usually take it three-dimensional. By chance the options are not matching in the case of three dimension, you go for the one dimension. Okay, and two dimension usually it is mentioned. And another thing, whenever there is ideal gas, you have to take the total electron gas, that is the ideal gas, whether it is mentioned or not, you have to take the total energy equals to kinetic energy, because there is no mention of potential energy also. So if the potential energy is mentioned, then you have to take that potential energy. Otherwise you can think or you can assume the potential energy is 0. Okay friends, and the room temperature is 300 Kelvin, whether it is mentioned or not. It is a usual assumption in physics. The next question is, in an ideal gas obeying MB statistics, there are n number of particles at a temperature T. The value of the internal energy E, U of the gas and the heat capacity CV at constant volume is U equals to 3 by 2 nkBT, CV equals to 3 by 2 nkB, U equals to half nkBT, CV equals to half nkB, U equals to n kBT, CV equals to nkB, U equals to 5 by 2 nkBT, CV equals to 5 by 2 nkB. In this question, both the one dimension and the three dimension, both the options are mentioned, but usually they don't mention the two things, that is one dimension and three dimension. So this is a contradictory question, but usually we take the three dimensional case. So we write U is equals to 3 by 2 nkBT, that is the average energy. Okay, because the individual average energy is 3 by 2 kBT. So for total energy, U equals to 3 by 2 into nkBT, that is the total number of particles. For one particle it is 3 by 2 kBT, for n particles it is 3 by 2 nkBT, and CV is del U del T at constant V, that is 3 by 2 nkBT del del T of 3 by 2 nkBT, that gives you 3 by 2 nkB. So option A is the correct option. The next question, 6 distinguishable particles are distributed over 3 non-degenerate levels of energies 0, epsilon, 2 epsilon. The total number of microstates of the system 750, 360, 529, 729. We have learned about the microstate in the previous lecture. That microstate is the state that will tell you the microscopic view or microscopic scenario of the system. Microscopic scenario means the individual positions of the particle, individual energies of the particles, and macrostates is the all over the macroscopic quantities, the total energy of the system, total temperature of the system, total volume, that are all the macroscopic quantity. So here you have to find out the total number of microstates of the system, where the number of particles are the 6 and the number of levels, energy levels are 3, and another thing is mentioned, these are all distinguishable particles. So distinguishable particles, we don't have to take the non-distinguishable case. So we have to take the Maxwell-Boltzmann statistics. Okay, so we will learn about Maxwell-Boltzmann statistics, but for this question it is not necessary to know Maxwell-Boltzmann statistics. It is a simple question of probability, that you have the 6 number of particles and you have 3 energy levels, and there is the total number of ways that you can arrange the particles, that is 3 to the power 6, that is 729, and this total number of ways that you can arrange the particle will give you the number of microstates. So the answer is 729. So option D is the correct option. Now in the same question, the total energy of the distribution for which the probability is maximum has been asked. So these options are 6 epsilon, 4 epsilon, 0 epsilon, 2 epsilon. So understand the question, the total energy of the distribution for which the probability is maximum. Okay, so you have to find out the distribution first, then you have to find out that for what quantity or for which probability this distribution is the maximum distribution. So here n is the total number of particles. Let us take that 0 for the 0 state, 0 epsilon state, there are n1 particles. For 1 epsilon state there are n2 particles. For 2 epsilon states there are n3 particles. Okay, so that the total number of particles, that is n1 plus n2 plus n3 equals to 6, that is the total number of particles. Now the particles are distinguishable, so we have to apply the Maxwell-Boltzmann statistics, or here we don't need to apply the distinguishable case. And also this is a simple probability question, that the number of ways of choosing N1, N2, N3 particles from 6 particles is W equals to 6 factorial divided by factorial N1 into factorial N2 into factorial N3. Now this is our thermodynamic probability W. So we get W as 6 factorial divided by N1 factorial, N2 factorial, N3 factorial. Now the question has been asked, the probability will when it be maximum. So W, this is our thermodynamic probability, this quantity have to be maximum so that we can get the answer. Now if this is maximum, means here this quantity in the denominator, that is N1 factorial, N2 factorial, N3 factorial should be minimum. Now we have to understand here, this is the probability concept. So we have to inspect the states, that we have to make some permutation and combinations to get the value of the product, that is N1 factorial into N2 factorial into N3 factorial as the minimum quantity. So let us take this three states, 0, epsilon and 2 epsilon, and we take the number of the particles in the state 1, that is N1 is 2, N2 is 2 and N3 is also 2, because the total number is 6. So 2 plus 2 plus 2 is 6. So what will be the product of N1 factorial, N2 factorial, N3 factorial? It will be 8. Now let us take another combination, that N1 is 3, N2 is 3, N3 is 0. We are getting this product as 36. We can take another combination, N1 as 1, N2 as 2, N3 is 3. So that the total number of particles, that is 6. And we get another product. And we can also take that N1 equals to 6, N2 equals to 0, N3 equals to 0. We get another product. But here by inspection we find this N1 into N2 into N3 factorial will be minimum when N1 equals to N2 equals to N3 equals to 2. Look here friends. So all other values will be greater than 8. So this is totally inspection. By inspection we are finding out that N1, N2, N3 the values will be same and this will be 2. So now we have to find out the what is the corresponding energy or total energy of the distribution. So we have to distribute the N1 particles, that is the at the 0th level there are 2 particles, at the epsilon level there are 2 particles, at the 2 epsilon level there are also 2 particles. So what we have to take? We have to take the total energy. So total energy of a system is given by E equals to N into Ni into epsilon I, okay, where Ni is the number of particles in that particular level epsilon I, and we have to sum of all the levels. So for the 0th level there are N1 particles, for the epsilon level there are N2 particles, for the 2 epsilon level there are N3 particles. So we get as total energy equals to 0 into N1 plus epsilon into N2 plus 2 epsilon into N3, that will give you N2 is 2, N3 is 2, N1 is 2, that is 2 into 0 plus epsilon into 2 plus 2 epsilon into 2, which is giving you 6 epsilon. So the correct answer is 6 epsilon. So option A is the correct option. Let us go to the another question. This is also a very important conceptual question here, and it is very common question in IIT JAM, GATE and NET examination. Okay, so the question is, a number of identifiable particles are distributed in a two-level system having energies E and 2E respectively. The average energy for the most probable distribution is how much? Now this is a question of the classical statistics or Maxwell-Boltzmann statistics. In the previous video, we have already discussed about some important mathematical concepts of the statistical mechanics, where we have defined the average of any quantity. We have to take, suppose we are taking the average of U. So we have to take the sum of U into function of E divided by sum over of function of E. That is, this function of E will give you the function of that particular probability function or probability distribution of that particular for that particular quantity. We have to find out the average value, and U is the discrete average values. So here the average energy for the most probable distribution is, suppose we are taking the N1 number of particles at the Eth level and N2 number of particles at the 2E level. So what we have to take, that is E average equals to E into N1 plus 2E into N2 divided by N1 plus N2. So let us take the N1 may be any number of particles, N2 may be any number of particles. So here N1 is E into e to the power minus E by kBt plus 2E into e to the power minus 2E by kBt divided by e to the power minus E by kBt plus e to the power minus 2E by kBt. So why we are giving this the expect average value of the energy? In the next video we will cover the concept of the average value of energy. So friends, in the next video we will discuss about the average values, how to find out the average energy values of a system, and we will thoroughly discuss about the concepts of Maxwell-Boltzmann statistics. So thank you friends, thank you for watching this video. Please like, share, subscribe the video, subscribe our channel, post your problems on our Telegram channel, that is Physics by IITians. All the best for the test to all our registered candidates. Thank you.